Hi, Assalamualaikum warahmatullahi wabarakatuh, and good day everyone. I am Ahmad Ikhwan bin Ahmad from Polytechnic Kota Kinabalu, Sabah, and I will present my research that is experimental study of flat heat pipe for cooling system using cross-flow heat exchanger. This is my partner, Sri Alifah binti Dahnian, and she also representing from the same institution as I am, that is Mechanical Engineering Department, Polytechnic Kota Kinabalu. Heat transport have been one of the most critical studies in the field of thermal engineering. Even though there are so many costly efforts have been taken to improve the efficiencies in the transportation of heat, the cooling system is still at the same notch. As a result of that, most common failure of the system nowadays occurred due to overheating problems. Thus, one of the practical methods that has been adapted into the area of thermal engineering to obtain a better cooling system is heat pipe. So what is heat pipe? Flat heat pipe is a device that can transfer heat from one place to another without the need for power source. Why heat pipe chosen for this study? It is because heat pipe is among practical method that has been adapted into the area of thermal engineering for better cooling system, and heat pipe plays a major role with the capability of transferring a large amount of heat over considerable distance due to its high effective thermal conductivity. Heat pipes are used in a variety of cooling applications. As we can see here, the example of application of heat pipes are central processing unit (CPU), spacecraft, pipelines, and air conditioning system. So the objective of this study is to investigate the design of constructed flat heat pipe fill up with refrigerant 134A and water as the working fluid in heat exchanger. Second objective is to test with different pressures, different volume flow rates, and different values of power supply. And lastly, to obtain efficiency of heat exchanger of this design. Based on previous study, Bar-Cohen 1983 through Ye and Chu 2002 state that the reliability of electronic component decreased by 10% for increasing every 2 degrees Celsius above normal operating temperature. Amolo et al. 2013 pointed out that computer dissipate a lot of heat and increase in the processor workload, resulting in high conductive adsorbent with heat sinks and then convection the heat to air or water. And convinced by Sonnen et al. 2008 that state flat heat pipe clearly works as a thermal spreader, providing a more uniform temperature distribution than the solid plate. Mehmet Esen 2004 in his study found that the gas R22 and R134A have better ability in absorbing heat, which further analysis on R134A will be carried on. And lastly, Sergey 2010 through Amolo state that amount of heat given off by computer depends on type and speed of the CPU, type, size, and efficiency of the CPU cooler, cleanliness of the CPU cooler, the number of PC cards installed, the type of PC cards installed, case design and number of type of case fans fitted, the processors the CPU is running, the type of graphic card makes, the design of the motherboard. And we can see here, as it deals with CPU and generate a motherboard, it is important to maintain the operation temperature of the CPU below a certain level. And this explains how important the study of heat pipe for an efficient cooling in the future. For the methodology, this design have four main parts that are: the first is container, the copper valve, the pressure gauge, and the copper tube. The material selection for this design is copper for the flat heat pipe, tubes, and cooling coil. The explanation was that copper is ideally suitable for heat pipes that operate between 0 degrees Celsius and 200 degrees Celsius. in applications such as electronics cooling. And the second material is Perspex for the container or the heat exchanger. We choose aluminium for the main platform, PVC for the water in and out pipe, and to be used with two working fluids that are R134A in the heat pipe and water in the heat exchanger. The selection of R134A as the working fluid also due to its lowest boiling point at atmospheric pressure compared to R22 and R410, and this refrigerant expected to evaporate at the lowest temperature possible. For example, electronic devices will not generate high heat all the time, so the heat pipe can operate continuously even at lower temperature. So for the experimental setup, the working condition will be in vacuum state. This is because in vacuum state, fluid will be boiled at a lower temperature, which then increase the level of heat being transferred. And in order to obtain the data, the heat was supplied to the heat pipe from a resistant heater and 6-point thermocouples were attached at 6 locations. The reading of temperature are recorded using MIDI logger. The picture on the left side is schematic diagram of the heat pipe experimental setup, and the right side is the actual heat pipe experimental setup. For the result and discussion, the result obtained is based on several tests on the design. By using the selected model, calculation will be carried out to determine the best value for pressure, mass flow rate, and power supply that give maximum amount of heat transfer. We also study the effect of changing the variables, that is volume of flow rate, 2 liter per minute, 4 liter per minute, and 6 liters per minute. Another variable is pressure of gas, 12 psi, 24 psi, and 36 psi. And the third variable is the power supply, 49 watt, 100 watt, and 150 watt. And to obtain efficiency of the heat exchangers. In the first experiment, the value of volume flow rate of water into heat exchangers has been controlled to get the idea if volume flow rate will influence the rate of heat transfer in the flat heat pipe. It was found that the temperature drop is high when the power supply is 150 watt and the pressure is 36 psi. And for that reason, calculation is taken at 36 psi and 150 watt data. The volume flow rate has been set to 2, 4, and 6 liters per minute, and time is taken from every 30 seconds until 300 seconds. The following data is referring at point T5 entry point of heat exchanger and T6 exit point of heat exchanger where the dissipation of heat take place. From the graph, the highest temperature drop obtained is at volume flow rate 6 liters per minute with 4.71 degrees Celsius. It shows that volume flow rate of water does affect the heat absorbed from the heat pipe into the water, where the amount of heat transfer is increasing for each addition of volume flow rate of water into the heat exchanger, which means the volume flow rate of water is directly proportional to the heat transfer. Next, the data is referring at point T2, okay, the point before entering heat exchanger, and T3 after exit point of heat exchanger. The graph shows the highest temperature drop obtained is at the volume flow rate of 2 liters per minute with 31.72 degrees Celsius. The data shows that the volume flow rate of water is directly proportional to the heat transfer because there is big amount of difference to the value of heat transfer for each addition of volume flow rate. In the experiment, the value of pressure given into the flat heat pipe also has been controlled to get the idea if value of pressure will influence the rate of heat transfer in heat exchanger. The experiment is running with 3 different pressures that are 12 psi, 24 psi, and 36 psi. From overall data taken, it was found that temperature drop is high when the power supply is 150 watt and heat transfer result obtained is maximum at 6 liters per minute, For that reason, this data here is taken at 150 watt and 6 liter per minute data. The volume flow rate has been set to 2 liter per minute, 4 liter per minute, and 6 liter per minute, and time is taken as usual from every 30 seconds until 300 seconds. The graph shows the effect of R134A pressure supplied to the flat heat pipe on the heat transfer. From the graph, it is shown that the rate of heat transfer is maximum, that is 1957.86 watt for both working fluid when the heat pipe is filling with 36 psi. And note that heat transfer for the volume of 12 and 24 psi is the same, that is 1870.44 watt, which giving the idea that heat transfer in heat exchanger will be more efficient when the amount of pressure is high. I believe the explanation is when high pressure is applied, high temperature will be obtained, which contributing to high temperature difference. As a result of high temperature difference, the greater the heat transfer obtained. The best parameter obtained for this experimental study is pressure 36 psi, volume flow rate 6 liter per minute, and the power 150 watt. In this project, flat heat pipe efficiency is determined from the maximum value of heat transferred in the heat exchanger, which is at point T5 and T6, since the condensation process is not occurred in the heat pipe itself. So effectiveness of heat exchanger calculation has been made, where the result obtained as shown here is 0.62. The value of heat exchanger efficiency will be compared with other study of flat heat pipe that use different design. Okay, the design one is our study, that is cross flow heat exchanger, working fluid R134A, and the efficiency of 0.62. The other design is using cross flow heat exchanger. The working fluid is water, and the efficiency of heat exchanger obtained is 0.52. And the last design we compared to is counter flow heat exchanger with R134A working fluid 2, and the efficiency of heat exchanger obtained is 0.45. So it can be stated here that R134A as working fluid with cross flow heat exchanger is better than the other design. This is mainly because the design of heat exchanger has larger surface compared to another design. So the larger the surface of conducting interface, the larger the heat transfer rate. Besides, it is experimentally proven that the type of cross flow heat exchanger is much more efficient than the counter flow heat exchanger. As for conclusion, a flat heat pipe made from copper was successfully fabricated and successfully tested with resistant heater, where the practical power it can accommodate is 150 watt. The effectiveness of heat exchanger is the indicator of the efficiency of flat heat pipe in transporting heat from a medium. And the best value of effectiveness of heat exchanger is 0.62, as the value is close to approach value of 1.0. And it can be stated here that this design applied cross flow heat exchanger and R134A as working fluid is the most efficient to transport heat comparing to other design. As for future study of heat pipe, the container material can be varied to study the effect of material towards heat transfer. Moreover, upcoming studies should be tested with different working fluid like gas R410 and R32, together with testing other alternative for the heat exchanger, as for example, using forced convection if the flat heat pipe to be used in application of computers. And lastly, the experiment can be tested in different places to find the best parameter of running flat heat pipe. And thank you.